start with the C part of the chapter. Now in the C part, we are going to learn about what do you mean by EMI. Okay, so you must have heard of those bank EMIs and all, but this is something else, guys. Here EMI means what? Electromagnetic induction. Electromagnetic
Should
induction.
we write all of this down?
You want, I will send you, otherwise PDF also. You want, you can write also, whatever you convenient. EMF, now guys, what do you mean by EMF? So EMF, remember, electromotive force, that is called as EMF, electromotive force. Now, so let's start with what is EMI. So see, I just told you some time back that whenever you pass current through a wire, what is developed around the wire? There is a magnetic field developed. Okay, but now they tried reverse of that. Meaning what, what they did? They passed magnetic field around the wire and then they realized that there is a current produced in the wire. So this process now of producing current in the wire by providing magnetic field around it, that is called as EMI, electromagnetic induction. Do you remember magnetic induction or induced magnetism? You are done in the 9th standard magnetism chapter. So yes, how the magnetic material will turn into a magnet, that was called as magnetic induction. This is called as electromagnetic induction, meaning what, we are generating what? Electro, meaning what? We are generating the current in it. That's why it is called as electromagnetic induction now. So see how this works. This is really very, very cool, this concept. You'll actually get fascinated the way it works and how they realized, all this. They came up with this. Now, let's say out here, I have a coil. Okay, so there is a circular coil, this coil, and the ends of this coil are connected to a center zero galvanometer. You know what a galvanometer is? Galvanometer will give you what? Direction of the current. And what do you mean by center zero galvanometer? Center zero means what? That the zero of the galvanometer is where? At the center. Meaning this galvanometer can turn this way. This galvanometer can turn. Wait a minute here. Oh, sorry. So this galvanometer can turn either towards the right side, or it can also turn towards the left side. Like so, depending upon the how the current is flowing, the needle can move either ways, guys. Left, right, any of them. Now, let's say now next to this, now here we have placed the magnet, guys, over here. So here you have got a magnet. This is say the north pole of a magnet, and then this is the south pole of a magnet. So let's see, this is as good as an experiment, guys. We are doing an experiment. There is a galvanometer kept in front of you, and we've got a magnet on the other side. So right now, initially, this magnet now it is at rest. Okay, this magnet is what? At rest. So when the magnet is at rest now, what do you notice? That your needle is at zero. Got it? I'll just make the summary over here. This is about the magnet, and this is about the galvanometer. So when the magnet is at rest, what happened to the galvanometer? It is at zero, isn't it? Now what I'm doing is, I'm moving this magnet. I started moving this magnet slowly towards this coil. Okay, let's say I'm moving the magnet towards this coil, guys, this copper coil or the solenoid, you can say. Now, when you started moving it closer to this coil, what happened, let's say the needle showed some kind of a deflection. And say the deflection was what, that the needle, so when you're moving the magnet towards, what did we notice? How was the needle going, guys? It was going on the right side. The deflection was on the right side, for example, like say this way. Okay, now what happened, then the magnet again came to rest. So you got it. Now you went on going closer to the coil. When you came very close to the coil, what you did? You eventually came to rest. But the moment your magnet again came to rest, what did you see? That the galvanometer will again go back to what? Zero. Now what you do? Now again pull this magnet away from the center. Okay, pull it what? Away from the coil. So meaning what? You are taking this magnet back away. Now, when you take it away now, what will you notice now? That the needle will now show what, deflection in which direction, guys? It will show you deflection in the left direction, left side. Now, then after you pull it away, again, when it went back to the original position, again, it came to rest. Again, the needle shows you what? Zero deflection. It was at a center 0. Got it? So these are the different positions that they have shown, like of the magnet and of the galvanometer. Now we'll discuss, guys, about what is the moral of the story. So what is the moral of the story? When was the galvanometer showing us deflection? Did you notice? Guys, was the galvanometer showing a deflection all the time? No. Look at it. When was it showing a deflection?
Sir, only when the magnet was towards it.
Correct. As long as there was a relative motion. See, as long as the magnet was in motion, whether you were moving it towards or you're moving it away, there was a deflection. But when the magnet comes to rest, whether it is nearby or far away, was it producing any deflection? No. So what is important now, that there has to be a relative motion between whom? Between the magnet and the coil, and then only you can produce the current. Otherwise, you can't produce the current. So if you feel that I will take this magnet, and I'll just put it inside this coil or something. Say you take a magnet and put it inside this coil. Iske andar dal diya. So that doesn't mean it'll keep on generating the current continuously. It'll not produce only. Because that magnet is at rest. That's why. Clear? So everybody's clear with this experiment, what we did. We are going to learn in some time how or why is all this happening. But right now I'm just telling you the observations, what happens, and okay. So you need what? Relative motion. Now see, when I say relative motion, look what it means. I have two options over here. One is what? I can move the magnet closer to the coil. I can move the magnet what? Away from the coil. Isn't it? So is there a relative motion? Do you see any relative motion between them? Yes, there is, right? Distance increases, decreases. I could do the same thing one more way. Look what I could do. I can take the coil towards the magnet, and again take coil what? Away from the magnet. Again take it towards the magnet. Again take it away from the magnet. And again what will be produced? Current will be produced in that. But guys, look at this thing now. Okay. If I'm moving both of them together on left or on right, will it make any difference? Will it produce current over here? Yes or no? It will not produce any current, guys. Why?
Relative motion is 0.
Exactly. There is no relative motion only between them. They both are moving. That's true. But there has to be motion between them. Okay. So even if you take a magnet in your hand, there is a coil, say here there is a coil in another hand. And if you're moving this magnet around it, or playing dandiya around it, something like that, still that will also produce the current, guys. Got it now? But the condition is what? There has to be relative motion. If you're just holding and dancing like that, if you're doing, then it will not produce any current, guys, because you see there is no relative motion. Got it? They are just moving, but there is no relative motion. That's why. So the most important thing is there has to be a relative motion, and then only it will produce the current. Jasapara, I have a question for you now. What if I move the magnet very fast towards the coil? What difference will you notice? If I move it very fast towards the coil, double the speed. What difference?
The galvanometer will move very fast towards the right.
Correct. So guys, she's correct. If you move the magnet with double the speed towards the coil, then your needle will also show you double deflection towards right, according to this data. Okay. Tanisha, what if I use a magnet with double the strength? If the strength is double of the magnet, what can you say about the deflection?
I don't know. Then maybe it will move with the same speed as the magnet.
Yeah, so if you're using double the strength, then again the deflection will be double. Same thing. Okay, there has to be double the deflection. So deflection and these things are directly proportional. You do something, more speed, more deflection, more strong magnet, more deflection, that way. Okay, so guys got it about this. So all this theory it was also put forward by a scientist called as Faraday. One second, I'll come to that later. So another thing now. So guys, now let's discuss about that while moving the magnet, why was it producing the current, guys? So see now what happens technically is that all these things now out here, these ones, they all basically contains what? Free electrons, right? There are free electrons out here. And if you're aware, every electron, guys, out here, okay, every electron behaves like a tiny magnet. It's a very, very small, weak, tiny magnet. And when this thing is moving, guys, okay, look at this. When this magnet is moving now, there are what, there are magnetic field lines this way. So when you're actually moving a magnet, what are moving along with the magnet? There are magnetic field lines also which are moving. But now look at this properly now. When I'm moving this magnet, say I started moving this magnet closer to this coil. You can see these magnetic field lines are cutting through it, those black color lines, they're passing through it. So when these magnetic field lines are passing through it, you know what happened to these electrons, red color which I have marked? They are tiny magnets, I said. So all those electrons, they will be pushed from one end, that is from end A to end B. Everyone got? Why are these electrons moving this way? Flow of the electrons. Because those are tiny magnets and then there is another magnet coming from there. So they all are pushed from A to B. Okay. Kashyap, I know you want to ask me why they will go repel only from A to B. Why not attract from B to A? So I'll come to that soon. Yeah. Okay. So guys, so right now we are assuming, we know when you're moving the magnet closer to the coil, the electrons will go away from A to B because you are moving it closer to the coil. But see out here now, look, let's say I kept on moving over here. Okay, I came so close. All the electrons went from A to B. Now when the magnet comes to rest, guys, okay, I'll repeat, see, when the magnet comes to rest, are those magnetic field lines pushing the electrons furthermore? No, now. You got it now, wherever it had to push those tiny electrons, it has already pushed them. Now magnet came to rest, so those electrons also came to rest there. But if I move this magnet away, meaning I'm releasing the magnetic forces from them, isn't it? So what will happen to all these electrons now? They will again start what, flowing back. They will again start flowing back from B to A. Now, Jasabara, if I tell you that I want to irritate these electrons, then what would you suggest to do to irritate them? You keep moving this front, back, keep on doing that, right? So what happened to these electrons? They'll go A to B, again come back, go A to B, again come back. Guys, are you understanding what kind of current is this produced now? AC or DC?
AC.
AC, alternating current. You see current, you know how current is reversing? It's going from A to B and again coming back from B to A. Again from A to B, again from B to A. So that's why this produces AC. Okay. Remember, we are talking about only AC out here, alternating current out here. Clear, everybody, about this whole thing? Okay, now there was this another. So all this theory, it was put forward by whom? By Faraday. So it is also called as Faraday's law or Faraday's explanation. So his name was Faraday. People call him Friday also in slang and Faraday also. Whereas technically his name is Faraday. What did Faraday say? In technical words, he said that magnetic flux. I mean, there has to be a continuous change in magnetic flux. Be careful, Aditya, when you read these words. Kabhi wrong pronounce kiya to gadbad ho jayega. Usually, people make a mistake there. So, guys, what does magnetic flux mean out there now? That while you are moving, look at this. What do you mean by magnetic flux? I'll tell you that first. So, say you have a circular loop or a coil, and the magnetic field lines are passing through it. So the magnetic field lines which are passing through it now, number of magnetic field lines passing through it is called as a magnetic flux. Got it? So let's say, for example, right now the magnetic flux is how much? 2 units. Then say some more lines are passing through it, 3 units. Then some more lines are passing 4 units that way. So what is magnetic flux once again? It is the number of magnetic field lines which are passing through the coil or which are linked with the coil. Okay. Got it? What is magnetic flux? Number of magnetic field lines linked with the coil is called as magnetic flux. Now, if this magnetic flux remains constant, guys, look at it. If this magnetic flux remains constant, will you be able to produce any current? Think about it. See, what if a magnetic flux is constant? It means your magnet is become constant. Na? It is not moving only in and out. You got it? Because see, when your magnet moves in and out, Dasavara, look at this. When your magnet is moving in and out, the magnetic field lines, like see, first there was just, let's assume first there was just first line, then 2 lines, then 3, then 4, then 5 lines going in, then again increasing, decreasing. Got it? So your magnetic flux increases, decreases. So the reason you want the magnet to keep moving is why, because only if it keeps on moving in and out, then only there is a change in the magnetic flux. So there has to be a continuous change in magnetic flux. Then only you can produce the current. Got it? You need a continuous change in magnetic flux. Then only you will be able to produce the current, guys. Clear, everybody, about the magnetic flux? So they can ask you in terms of magnetic flux. So magnetic flux basically means what? Number of magnetic field lines which are passing through it. Clear? And you need a continuous change in the magnetic flux, so that you can produce the current. Now see this part now. Like remember I told you when I move the magnet closer to this coil, the current is induced. Okay, and I said electrons are moving away, so they may be moving away and closer. How do we figure out that, guys? Now see this whole concept now of EMI. You know what it is based on? It is actually based on law of conservation of energy and work energy theorem, guys. Okay, or you can simply say work energy theorem. Look at this idea now. This is really good. Look, see what are the energy conversion in this experiment? We are converting mechanical energy into electrical energy, isn't it? You're moving the magnet in and out, so that's mechanical energy, and you're generating electrical energy, current. But when I say mechanical energy, mainly what form of mechanical energy? Potential or kinetic?
Kinetic.
Correct, kinetic energy. So you can say more or less I am basically converting kinetic energy into whom? Electrical energy. Kinetic into electrical. Now if I am converting kinetic into electrical, it means kinetic energy will start decreasing and electrical energy will start what? Increasing. Correct, na? Because we are converting kinetic to electrical. For kinetic energy to decrease, the velocity of the body should decrease, right? Because mass will not change, mass will remain constant of a body. You remember formula of kinetic energy, half mv squared. So if its velocity will decrease, then it will be kinetic energy will also decrease. When I say velocity decrease, what does it mean? The body must slow down, right? Now tell me, over here, north pole of a magnet, when I'm getting the north pole of a magnet closer to this coil over here, can you tell me which pole will it induce here at the end?
South pole.
Guys, what do you want the magnet to? Slow down. Who will slow down? Only if what is there, Aditya over there? Opposing force, right?
Yeah, repulsion.
Exactly. Opposing force. Matlab, you said what? Repulsion. That's correct. I'll write that word here. Very good. It's called as repulsion. It means what, that this north pole will induce which pole out here, guys?
North
pole. Exactly. Got it, now? Now, if a north pole is induced over here, guys, if a north pole is induced, what would be the direction of current in the coil? Clockwise or anti-clockwise? We had done it last year.
Clockwise.
Hey, bhai, Anguta Chap method, guys. Nidhi, do you remember? Tanisha? If the polarity is north pole, what must be the direction of the current?
N of anti-clockwise.
N for anti, exactly. N for north pole. Remember or no? See, same thing, na? These are circular loop only, na? Basically, here pe. So if it is N, what will be the direction of the current over here? Anti-clockwise, guys. Got it? So it will be anti-clockwise direction. That is the direction of the current produced. Just about understood? Guys, this concept now is also called as what, Lenz law. Okay, what is it called as, guys? Look, Lenz law, named after another scientist now. Lenz's law. So Lenz law states, that if you take the north pole of a magnet closer to the coil, it will induce a north pole only over there, guys. Aditya, clear now?
Yes, sir.
Okay. Now, guys, there is one more rule. Okay, this rule was put forward by Fleming. So see, you already did, which law first? Right hand, right? Fleming's left hand rule. Guys, now since he had two hands, he had one more rule. He made one more rule. This rule is called as Fleming's right hand rule now. So guys, luckily this guy had two hands only. So Fleming's right hand rule states what, now. First thing, what do we use this rule for? We use this rule to identify the direction of the current. This is what we use it for. To find out what is the direction of the current in a generator actually. But now we are not doing that. We are just learning the rule. What is Fleming's right hand rule? So again, same thing. You have to make use of your right hand. Okay. Again, another yo in the right hand, guys. All the fingers are also the same that we use. So we go to use which fingers here? Forefinger for what? Will represent what? Magnetic field. Then your thumb will represent what? Thrust or the force. And your center finger will represent what? The direction of the current. Center finger will represent the direction of the current. So we are using this rule to identify this direction of the current. Again, how to use it? So I'll just tell you what the rule is. You have to stretch your forefinger, your center finger and your thumb such a way that they are mutually perpendicular to each other. Got it? Now, if your forefinger is in the direction of the magnetic field, guys, okay. If your center finger is in the direction of the current, however, say current is going, sorry. If your forefinger is in the direction of the magnetic field, if your thumb is in the direction of the force, however the force is applied, like left way or, upwards or this way, you'll have to keep turning your hand accordingly. So always first go for the magnetic field, then look at the direction of the force. Say my force is going from right to left, this way. Then what would be the direction of the current, guys? Downwards, right? You see the center finger going down. Okay, now if you turn your hand upside down like this way, now see again magnetic field is north to south, right? Going into the camera. How is the force? Force is going from left to right, this direction. Then what's the direction of the current in the wire? Upwards. Got it? So these are the different, you can apply. So you just need to learn the rule. You will not have any application of this rule. But that is what it is used for, to identify the direction of the current. Clear? One second. I'll give you one example. Yeah, one more thing. If they ask you what is the difference between Fleming's left hand rule and right hand rule, what will you write? Left hand rule is used to identify what? Direction of force. And right hand is used for what? To identify the direction of the current. Okay. Don't write the difference of left hand and right hand. Okay? They will not consider that, though it is a difference. That would not be considered as a difference, though. So guys, you have to learn in this chapter C part, you have to learn only 10.13 and 14. Okay, that much only. 13 and 14 completely. Nothing else you need to learn. And I'll tell you which questions are there in your portion from the exercise. Exercise 10C. ये नींव है कि चला गया? Exercise 10C. Question 1 to question 16. Okay, guys, these are the questions you have. So got it now. The homework would be exercise 10B, 1 to 6. And this is 1 to 16. These are the only questions in your portion. Okay. Guys, on page number, go to page number 258 now. We will do some questions from here right now.
Sir, I did not understand Lenz law.
See, the statement they have given or the meaning of it?
The meaning. I mean, what is it used for?
See, what does Lenz law state, that the pole which you're using, like whatever pole of a magnet you're approaching the coil with, it will induce the same pole at that end.
So how is that used to find the direction?
Because if I come to it's a north pole, then I know it's anti-clockwise. If I come to it's a south pole, then I come to it's a clockwise. Actually, you're using clock rule also along with that, not just the Lenz law. So इसमें भी एक बार controversy होता है when they ask which rule you use to identify the direction of current. So first priority is Lenz law, or right, Lenz and clock rule both.
Sir, but anti-clockwise से आगे पीछे का क्या है? I don't understand.
नहीं देखो एक मिनट को अगर if you're moving the magnet, one second, मेरा ये cursor खराब हो गया है. One sec. If you're moving the magnet, say you're moving the magnet like this here, this way, over here. So because you're getting north pole closer to the coil, what will be the pole induced over here? North pole. Now, if it is north pole, what should be the direction of the current? Anti, na, you said.
Yeah.
So current will flow this. Oh yeah. So your needle will deflect this side.
Got it.
Got it? Okay, see now page number 258. Jasapar, I'll tell you which ones to do. You try reading and answering them now. You can give the answer in your own words, it's absolutely fine. Third one. Kashyap, we can close the meeting. हाँ चलेगा अभी. खाली इसी बना बड़ा हो जाएगा file.
Recording switch off.
Yeah, you can close the recording. Yeah. Khushi.